a unit direction vector in the direction of A, I need to discuss something with you first. So what I want to discuss with you first is what happens when we take a vector, or let's be more specific. What happens to a vector's magnitude or length when we multiply it by a scalar? Okay? You think it increases, right? Depends on the...
Or it depends on if it's greater than 1.
Right. Would depend on the scalar, right? So we know already, right, this vector here, if we find the norm of it, this is going to be the norm of A, or the magnitude of A. You see how you start switching language around. It's going to be the square root of 4 squared plus 0 squared plus 3 squared, which is the square root of 16 plus 9, 25, right? So this is 5. So this is famous. OK. What about, that's a 0, just in case. So what if I take the vector and I double it? I say the norm of 2A. Well, that's really saying the norm or the magnitude of this vector, 8, 0, 6. So that's what it means to take a vector, multiply it by a scalar. You distribute the scalar into all those components. So we just multiply 2 by all of these. OK. And now we have this new vector. Well, here we go. What's its length? The square root of 8 squared plus 0 squared plus 6 squared, which turns out to be square root of 100, which is 10. So the question is, if I have a vector of a given length, and then I multiply it by a scalar, what's the length of the new vector? And I think you know the answer, right? It's the scalar that you multiply by the, correct, multiply by the length of the original vector. That's what happens. So once you agree to that, once you agree to this, that if you have a vector A and you multiply it by some scalar K, let's make that clear. So A is the vector, and K is the scalar. Oops, sorry. Then what we know is that this relationship is true. It's sort of fun to try and prove that. It's not that bad. It amounts to factoring out a k squared from underneath the square root. I'll tell you again, in your mathematical futures, you'll read in textbooks, they'll say, oh, the proof is left to the reader. Anyone ever read that in a math textbook ever? OK? It happens sometimes. So just be prepared for that in your futures. OK. That's right. That's right. That's what you know. OK, so here we are. Here's the vector 4, 0, 3. We know the length of that vector is 5. The question is simply this. Here's the magic, or the most important question now for getting unit vectors. What scalar should we multiply vector A by so that the resulting vector has length 1? That's what we want to answer. If we can answer that question, then we know how to find a unit vector in any direction we want. You think you know? What do you want to multiply this vector A by? 1/5. That's right. We want to take the vector 4, 0, 3 and multiply it by 1/5. We end up with this vector, 4/5, 0, 3/5. We can verify quickly that it has length 1. So you get 4/5 quantity squared plus 0 squared plus 3/5 quantity squared, square root. That's the square root of 16 over 25 plus 9 over 25, which is just the square root of 1, which is what we wanted. This thing turned out to have the length we desired. All right, so we can finish by saying that in general, 1 over the norm of A times vector A is a unit vector in the direction of A. It's not terrible. It really isn't. But that's the basic idea. Just a quick comment before we finish. If you look at this expression, it's sort of fun to ask yourself, hey, what in that expression is a vector and what's a scalar? Right? So this is where these things start to have very different meanings. Yeah?
When you say spell scalar, you use U or A, right? Most times it says A.
I'll check it. I probably spelled it wrong. Scalar should be AR. Sorry. All right. Anyway, luckily, no one's going to watch this video really, so it'll be all right. Okay. Fair enough. I could edit it. All right. But anyway, I'm looking at this expression, and it looks like, I mean, some of us look at that and say absolute value A, there's A. Things start to look maybe not that different. They really are. This is a very different thing. This A up here is a vector. It has a set of components, right? This norm A here is just a number. This whole thing is just a fraction being multiplied into a vector with however many components vector A has. So it's sort of a good experience. As you start to get, sink your head into problems in this course of multivariable, you should start to look at things and say, hey, what's a vector here? What's a scalar here? Okay, that's what's going to matter. All right?